Hi there, I'm Mr. Troja, and I'm going to be talking about the sun structure. This is part one in a two-part series about the sun structure, and we're mostly going to be talking about the atmosphere, the outer edges of the sun. So, a couple of statistics about the sun. I'm not going to talk about all these, but highlights that we could line 110 Earths up right next to each other to get the diameter of the sun and fit 1,300,000 Earths inside the sun. This is an overall of the solar structure. We will be going through these through the two parts of the video. Um, Specifically, this video is going to be talking about the chromosphere, the photosphere, and the corona, those three outer layers here. So here's another picture of this. We have the core, the radiative zone, convective zone, and then the photosphere. We'll talk about sunspots a little bit today. Some of these other ones we'll talk about in other videos. So the solar atmosphere, again, there are three layers that we'll be discussing in this video: the corona, the chromosphere, and the photosphere. The corona is the outermost layer, gets extremely high temperatures, and is only visible during a total eclipse. Here's a picture of it happening during a total eclipse. The moon is if the people that were on Earth taking this picture were in the shadow caused by the moon, and you can see the corona of these bright looking flare pieces coming out from around the outside of it. So only visible during a total eclipse. The chromosphere is just below that, close to the center of the sun, and definitely cooler, not 1.7 million, now 28,000, and it is also visible during a total eclipse. Doesn't have quite as distinguished as that last corona picture, but we are looking at here the outside edges. We have this reddish color due to the alpha particles that are emitted, and these little things that are shooting out, spicules that are little jets of hot matter. So the next one down is the photosphere. It means sphere of light. That's the photo part. And this is the outer layer of the interior of the sun, or the lowest layer of the atmosphere of the sun. So the corona and the chromosphere are both kind of unclear, much like if you think about our air is clear, and if you were outside of the Earth, you'd be looking at the surface of the Earth. So outside of the sun, the surface that we see is the visible part of the sun. Now, if you look very close to it, and these weren't discovered until we had satellites, they see these granules, so we'll talk about those here. So what is a granule? If you notice, there's an image of the sun and it doesn't look nice and smooth. If we were to animate that surface, we'll see this, and it almost looks like it's boiling up a little bit, because that's really kind of like what it is doing. So what is this granulization? So observed in the 1970s, these granules, which we go back, are these areas surrounded by dark, they're lighter areas. So they can be as large as one of the continents on our Earth, and lasting for several minutes. There's the light and the dark is based on the different temperatures of the surface at that point. So what actually happens is we have these hotter and cooler temperatures in the hotter regions. We have a convection going on, and we'll talk about that a little bit more in another video. But the idea is that the hotter the fluid is, it's less dense and it rises to the surface. And as it cools off, it becomes more dense and it falls back down towards the center. And so we have these areas in the center that are rising up, and then they go to the outside, and then they fall down. And so that's how we get these shapes that are called granules, as we have the gas rising up into the center, and then it rolls across and comes back down into these lower temperature zones, which are the darker colors. Here's a picture of the photosphere, and this picture in particular has these areas here that we call these sunspots. If you were to look at, I'm going to go to the spaceweather.com, and we can see a picture of the sun today. And so spaceweather.com, there's a whole lot of things that you can find out here. But here's a picture of May 11th. That was today's picture. And so you can see there's no sunspots. Interestingly, we are in a period of minimum level of sunspots. We're at about the lowest you can get if you looked up at the sun. If we were in class, we would find a sunny day and we'd look up at the sun with some filters, and it would just look yellow. We wouldn't see any of these sunspots at the moment. So there is a cycle of sunspots. So the last maximum was 2014, and that was actually even a lower maximum. There were periods in the 90s where there were a lot of sunspot cycles. But the sunspots appear within 30 degrees of the equator. If you think about the equator as 0, as you go closer up towards the north or south pole would be 90 degrees. So part way up is 30. And so during a time of the minimum, if they do show up, they're a lot farther from the equator. And during time of a maximum sunspot cycle, there's going to be more towards the equator of the sun. So it's about 11-year cycle. It's not always consistent. So here there's a period of time, the Maunder minimum, that was actually a 50-year period of no sunspots. And during that time, it's a possible climate link, but don't have complete facts on that. So what are these sunspots or these solar spots caused from? They're dark in color, and they're dark, they have that lower temperature. Much like we talked about, the granules had the lower the temperature, had the darker coloring, and that's what a sunspot is. It has this lower temperature, and it's caused by magnetic storms. So what's happening? Here's the sunspot, and convection is this moving of the low dense and high dense material. The lower density moves up and the higher density moves back down. So out there in the lighter regions, we have the 6,000 degrees Celsius, the darker regions 4,000. That's where that sunspot would be. So convection, when it's down in the interior of the sun, it heats up and rises out to the center, and then when it cools off from the radiation that leaves in the form of photons towards the Earth, it takes that energy away, and then that cools down and goes back down towards the surface again. So what's actually happening in a sunspot? Said a little bit ago, it's caused by magnetic storms. So underneath that spot is a bunch of twisting magnetic field lines that cause the hotter plasma not to be able to rise up in that location. So since we're talking about magnets, this is a picture of a magnetic field. This would be a bar magnet with a north end on one side and a south on the other side. And this is what the magnetic field lines look like. These would be iron filings that are lined up in a magnetic field. That's important because that's what's happening in these sunspots. Every magnet that you have has a north and a south pole. And so these sunspots can come in pairs. When they come in pairs, one of them ends up acting like the North Pole and one ends up acting like the South Pole, and they get these magnetic field lines. And we actually see parts of the sun that extrude out along those lines. So the last thing I want to talk about with sunspots is Galilei, back in 1612, actually discovered that the sun is rotating. And not only does the sun rotate, as far as the fluids in the sun, but it rotates differently from the equator. The equator actually rotates around at a rate of 25 days for one solar rotation of the equator, but on the poles, it actually takes longer. It rotates slower at 36 days, which is really interesting. And how I could tell that is the way that the sunspots moved. And, if you look at this two-dimensional image, it's pretty hard to tell that it's a sphere, but the other way that they looked and determined it was a sphere, if you look at this sunspot, it's nice and circular, but as it goes around to the edge, it starts to stretch out and get a little oblong. And so that was part of the evidence that made them believe this was spherical. All right, so in our next video, we'll talk about some other activity that goes on in the sun. We'll continue on the outer edge of the sun, talk about prominences, flares, filaments, solar winds. And here's a final cool solar image to leave you with.